Today's speaker is Yantao Wu of Syracuse University, and apparently from what he said a little while ago, soon to be of Johns Hopkins University. He's an undergraduate here. And his talk will be on the Halperin conjecture in small formal dimensions.
Okay. Let me share the screen. So can you guys see the slide? Okay, so I will begin now. So good afternoon, everyone, and thank you so much for coming to this seminar and listen to my presentation. So the title is the Halperin conjecture in small formal dimension. My name is Yantao Wu. I'm a Syracuse University senior, majoring in mathematics and physics, and the mentor is Professor Li Tina in Syracuse University Math Department. And this research project is funded by SOURCE program. It is a synchronous of Syracuse Office of Undergraduate Research and Creative Engagement. It's very helpful if any undergraduate student would like to do some research. And I would like to also thank Professor Manuel Ammon and Professor Claudia Miller for their help in my research. So let me begin with basic definition. So we start with the graded polynomial algebra. It is just a polynomial ring. When we give any variable xj a grade of it, we denote by two vertical lines with xj inside. It's not absolute value, it's just the grade or degree of xj. So we also define something to be a regular sequence. We say a polynomial, a chain of polynomial, they form a regular sequence if each relation or each polynomial is not a zero divisor in the quotient by previous polynomial. This definition is very complicated, so I will give you two examples, one example and one counterexample of it. First, we have a doubly generated polynomial algebra Qx1, x2. The first relation is x1 squared minus x2 squared. The second relation is x1 times x2. And we can see that the second relation x1, x2 is not a zero divisor. How can we prove that? We suppose that x1, x2 times a polynomial p is a multiple of x1 squared x minus x2 squared. Then because x1 and x2 are prime in the polynomial ring, so we can show that the polynomial p is also a multiple of x1 squared minus x2 squared. So this will show that it's not a zero divisor. And the second is non-example. The first relation is x1 squared. Second relation is x1 times x2. We can see that the second relation is a zero divisor because the square of it will be x1 squared times x2 squared. So there will be a multiple of x1 squared. So intuitively speaking, a sequence of polynomial form a regular sequence if there is no redundant terms. In linear algebra, we say no redundant term is like linearly independent. But here we have multiplication. So being something is not redundant, we have a complicated definition. Now, how can we mute it? Well, just go on. So we will define the main object of positive elliptic algebra. I will first define it from the algebraic version of it. We define something to be a positive elliptic algebra with synchrony PEA. It has three requirements. First is that each relation is a homogeneous polynomial. Second requirement is that the polynomial form a regular sequence, and we have just seen the definition. And third requirement is that each grade of xi, xj is a positive even integer. I need to expand on the homogeneity and even here. The homogeneity is different from what we say a homogeneity in terms of word length. The homogeneity here means that in a polynomial, each monomial has the same degree. When usually we say homogeneity in terms of word length, it means that each monomial has the same word length. A different meaning here. And as you can see in the example, the x1 squared minus x2 squared, it is a homogeneous polynomial because each monomial has the same degree 4. And also we have another requirement. The grade of each variable is an even integer. It seems weird. Why we need even? Why we just can't scale everything by one half? The reason is that the even is connected to something like positive Euler characteristic, and I will talk about that later. But in addition to that, we require the grade to be even integer. It is also helpful for us to compute the formal dimension. And as you can see in this example, the first relation is x1 squared minus x2. The second relation is S2 squared. It's clearly its homogeneity and from a regular sequence, and each generator has a positive even integer grade. And we can see that it is a vector space, and when we write the basis out, it's 1, x1, x1 squared is also x2, x1 cubed is also x1 times x2. And it turns out that this vector space is isomorphic to another vector space, which is simply generated polynomial algebra with one relation called x1 to the power 4. And it's interesting that we have two different presentations which represent the same object. And I will come to that later, how we choose one good representation. Here are some very many equivalent properties for a positive elliptic algebra. First, we want something to be a regular sequence, and it turns out to be that equivalent to property B. Scroll dimension is 0. And we can just compute that because the number of generator k is k, and the number of relation is k, and the relation from a regular sequence, so the core dimension is just k minus k, so 0. And third, H star has a finite dimension when we treat it as a vector space. As you can see in the example, it's a vector space with dimension 4, it's finite. And last, we introduce something new called formal dimension. The formal dimension have weird definition. It's the sum of degree of relations minus the sum of degree of generators. This can be weird. Why we define that? I will explain later. But first, we can see that the formal dimension is a well-defined term. As in the example, when we use the first presentation, the formal dimension here is just 4 minus 2 plus 8 minus 4, which is 6. And if we use the second presentation, 2x1 portion by x1 to the 4th, we compute its formal dimension, which is 8 minus 2, is also 6. It is well defined. So as you can see in the previous example, we have two different presentations which describe the same object. So it's natural to ask why we just pick one good presentation for it. When we say good presentation, it means that it looks simpler, but it really means that we can have less generator here, one fewer generator for the second presentation. And it introduced something called pure model. And pure model have very long definition, but the essential part is that we require each relation to be at least quadratic. It is, as we say, Q with power at least 2. So each monomial is at least quadratic. So what we need is that, I will explain it. First, if we have a rational number term, I mean a constant term in a relation, then for degree reasons, that the relation itself must have degree 0. So any term must be a rational number, which means that the relation itself must be a constant. This will fail the regularity. And if we have a linear term, let's example here, we have a linear term in one relation, then we can have an algorithm to perform the change of basis. And it turns out that we can cut down the number of generator by 1. So it will give one simpler description here. So if we suppose that we have repeated this process and then at the end, we have all the relations here are at least quadratic. And this pure model is beautiful because we have many good properties. First is that we can assume in part 1 and part 2, the degree of generator and the degree of relations, they are in ascending form. And third, they give a lower bound of the degree of relations. And the property 4 says that the formal dimension is well defined. It's still in a new presentation, is formal dimension the same. And the property 5 says that a strong algebraic condition. It is a very complicated tool, and I will not give a very detailed description about it, but intuitively it says that the degree of generators as a whole gives some restrictions on the degree of relations. And before moving on, let's review some of the properties. Many properties only focus on the degree, as you can see. They only consider on degree instead of is how it looks like. And the reason is that we can perform a change of basis frequently, add one relation to another, multiply something else to another. So it turns out that it's good to just look at the degree because the degree is fixed. And because it's background knowledge, to some extent, this knowledge shape our strategy in problem solving. We only consider its degree. So let's consider this problem in front of a logical version. So the homotopy group pi star, well, it's with the star is 1, so pi 1 is the fundamental group, and each element is the equivalent class of loop. And if we tensor product this homotopy group with a rational number, actually we lose some information about it, but this process also reveals some deep structure. And if we want the dimension of rational homotopy group to be finite, and we also want oriented and closed. So this manifold is called rationally elliptic. If in addition we have the positive Euler characteristic, then we say some manifold is positively elliptic. And this part, positive Euler characteristic, is why we have even integer for the grade of variable x. And as you can see, we have just introduced something positive elliptic algebra. And here we have positive elliptic space. They have very similar name. Actually, they are closely connected to each other. The theorem says that given a positive elliptic space, we consider its rational cohomology algebra. And this algebra is positive elliptic algebra. So let's first explain why we use the H star, because it's a cohomology algebra. So on one hand, positive elliptic space is the underlying manifold of a positive elliptic algebra. And on the other hand, positive elliptic algebra is the algebraic structure of some positive elliptic space. And the last property here about formal dimension as it plans. Why we call it a dimension? Because we can just call it another parameter. It's a dimension because it is a dimension of some underlying manifold M. So if we have formal dimension 6, it means some underlying manifold has dimension 6. When we say formal dimension at most 20, it means that the dimension of manifold is at most 20. And also by Poincare duality, we can also show that this formal dimension, it is the greatest integer that h to the degree j to the degree d is not 0. And after that, h to degree d plus 2, d plus 4, anything else, anything beyond that will just be 0, be a 0 space. So the formal dimension also gives a maximum of degree for each generator. The last 5 slides give an introduction on the rational homotopy theory. This book is very helpful. In chapter 32, it talks about some of the structure of the positive elliptic algebra. And in chapter 39, this book lists 17 open problems in this area. One of this is the Halperin conjecture. I will not give this original definition of the Halperin conjecture because it's a very terminology that really I don't know, but I will work on that from the algebraic method. Well, before moving on, do you have any questions at this stage? So if there's no question, I will just move on. So the algebraic version of Halperin conjecture is because in 1982, they reformulated the conjecture into an algebraic description. It says that positive elliptic algebras do not admit non-trivial derivations of negative degree. Since I have not defined what is a derivation here and what is a negative degree, I will give a definition here. A derivation, delta, is a linear map that satisfies two properties. First, that it changes the degree by some integer. We denote by two vertical lines of delta. It means the degree, not absolute value. The degree can be positive, 0, or negative. And second is the Leibniz rule. This is a general description of Leibniz rule because we have a -1 to the power of degree delta times the degree of A. That is of course since we have switched the order of delta and A in the second term. And I need to explain what this inclusion says. It means that if we have a variable x with degree n, the image delta x will have degree n plus the degree of delta. Since we have worked on the positive elliptic algebra and we know that each variable is even graded, so in general, the -1 to some power will always be a +1 if we just work on positive elliptic algebra. Since this definition is a little bit abstract, I will work on some example, as you can see. First, this example shows that a positive elliptic algebra may admit a derivation if the derivation has positive degree. So this example is doubly generated with two relations, x1 squared plus x2 squared. Second relation is x1 times x2. By the previous process, we can see that it is from a regular sequence of even degree and satisfy homogeneity. We define something to be delta, which map x1 to x squared and map x2 to 0. Notice that the 0 can be any degree, so the degree of 0 is nowhere defined. We can arbitrarily define a degree of 0 here. So we can see that it is a derivation on the polynomial algebra with positive degree 2. And we want to show that this delta descends to a derivation on the quotient space H star. Well, we can check that it preserves the ideal. It maps the x1 square plus x2 square in the ideal, and a map x1 times x2 in the ideal. We can work on that. First, the delta x1 square plus x2 square, the image will be 2 times x1 to the cube. And x1 to the cube is actually x1 times the first relation minus x2 times the second relation. And delta x1, x2 will be x1 squared times x2, which is x1 times the second relation. So we can check that it is a derivation on the quotient positive linear algebra. And we have more examples. These two examples here shows that if something is not positive in linear algebra, then it may admit derivation with negative degree. They are not positive in linear algebra for different reasons. First, in this first example, it's not positive in linear algebra because it's not the relations do not form a regular sequence. As you can see, x1, x2, the square of it will be a 0. x1 times x2 will be a 0 divisor in a quotient by the first relation. We define delta x1 to 0 and define delta x2 to be x1. So this derivation will have degree -2. And we can check that this delta descends to a derivation on the positive linear algebra because it preserves the ideal. Delta x1 times x2 is clearly 0. Delta x1 squared is clearly 0. And delta x1 times x2 is just x1 squared. So it is checked to be correct. And the second example is a little bit different because we have odd degree. So this means that the Euler characteristic of the underlying manifold is no longer positive. And definitely this algebra is not a positive elliptic algebra. We define image of x2 to be 0 and define the image of x3 to be x2. And recall that image, the degree of 0 can be any. So this is a derivation on a polynomial algebra with degree -1. And notice that by the Leibniz rule, we have a negative to some power. Let me go back. The negative to the power of degree delta times degree of a. So in this example, when we compute delta of x3 squared, we have a negative sign here, which means this will become 0. If x3 has even degree, there will not happen. So by the three example, we see that positive linear algebra can make the derivation with positive degree. And if something is not positive in linear algebra, then it can make derivation with negative degree. So it is natural to ask, what is the remaining situation? If something is positive in linear algebra, whether or not it can make derivation with negative degree. And the conjecture says no, a positive linear algebra cannot admit the non-trivial derivation with negative degree. So let's work on one of the simple example here. So consider this positive linear algebra is doubly generated with two relations. Here is satisfied regularity, satisfied homogeneity, and even grading. We suppose that there is a derivation with negative degree. Since x1, x2 is the minimum non-trivial degree, so if the delta itself is non-zero, then delta x1 and delta x2 must be degree 0, which means they are rational number. So by linearity, 0 is just delta 0. And we can write the 0 as the x1 times x2 in the quotient space and use Leibniz rule to explain that. But when we look at it again, this is a constant number times x2 plus a rational number times x1, it becomes 0. But on the other hand, we know that x1 and x2 are linearly independent. So this means that delta x1 and delta x2, they are both 0. So by the Leibniz rule, the delta itself, we explain that the delta itself must be 0. So in general, we have a general property that it is a lemma in Emma and Tina's recent paper. It is showing that if delta has degree 0, then delta x itself must be 0. So this example is just one special case. So this is when we talk about the main theorem. Tina and I worked on the theorem to prove that the algebraic Halperin conjecture holds for formal dimension up to 20. Let's recall that the H star look at the quotient and the formal dimension is just a degree minus degree. So here are some previous work. There are many cases when the Halperin conjecture are already verified. The first is that it is true when the number of generator k is 1, 2, or 3. And it also proves that the Halperin conjecture holds for a reduced case. This means that the Halperin conjecture is generally true. And if we look at the general case, we might hope for an affirmative answer. And the third is the Emma and Kina, their recent paper. They proved that the algebraic Halperin conjecture holds up to formal dimension 16. And we will just focus on this strategy here and push up the formal dimension higher. And actually, there are many cases when mathematicians work on different directions, and the conjectures are also proved to be true in many geometric conditions, but it is not our strategy, and we will not focus on that. Our strategy from the previous work is talk about the degree sequence and something to be split. The degree type is that the degree of generator together with the degree of relations. It is important because as I have just described, we can frequently permit a change of basis or switch two variable to relation if we have the same degree. Even if we can do many changes to that, the degree is fixed. So the degree type for positive elliptic algebra is already fixed, whatever changes basis we do. And the split is another description. Intuitively, it means that a positive elliptic algebra itself contains another positive elliptic algebra. But the rigorous definition says that it splits if we have short exact sequence 0 to k star, to h star, to q star, to 0, where k star and q star are non-trivial PA. If we have a pure model h star, if it's a pure model, then it splits if the first L relation depends only on the first L generators. So it's another description. We say something probably contains another positive elliptic algebra. So the split here is just an intuitive description of something to be reducible. If a positive elliptic algebra splits, it means it's reducible to another with two positive elliptic algebra. But why split is important? Because it has we have a Markov theorem. The Markov theorem says that if the PA splits, and if we have a positive elliptic algebra, then either k star or q star must also have a non-zero derivation with negative degree. Well, this means that if PEA is reducible, then the negative degree derivation is also reducible. And if in the process we do some strong induction, we assume that in each step, there's no non-trivial derivation with negative degree for formal dimensions really smaller than n. Then we work on the case where formal dimension is equal to n. So the Markov theorem says that in each step, we can assume that there's no, we can assume that the positive elliptic algebra do not split, and very strong property. If something splits, then we can get something smaller. We can get smaller k, smaller formal dimension, and a small dimension. Actually, we can use any criteria. Here we use the induction based on the formal dimension, but anyone else can do almost the same induction step with number of k or the number of dimension. Markov theorem is generally true and very helpful to do some research in this area. So there are also many other useful tools from Anna and Kina's work. I will just copy it here. The first is the landing zero lemma. As we have just seen, it means that if the image of something has 0 degree, it is landing 0, then the image itself must be 0. And the k minus 1 lemma here says that if the delta vanishes on k minus 1 generator, then the delta must also vanish on the remaining generator. It's also equivalent description to say that the rank of delta cannot be 1. If it's at the most 1, its rank must be 0. If the rank is at least 1, the rank must be at least 2. So I will go on that later. And here's another lemma called degree inequality. This is true because we assume that they do not split. This gives a lower bound on the degree of relations, and it's very helpful because the lower bound on degree of relations allow us to push up the formal dimension higher. I will not give a proof of the degree inequality, but I can explain it in one simple case that if we do not have this property for I equal to 1, so if we assume that U1 is degree of U1 is smaller than degree of x1 plus degree of x2, then for degree reasons, we can check that U1 itself must be a polynomial that only depends on x1. They will contradict to what we say something do not split. So that's why we have this inequality. So I will give something new. Kina and I proved 2 new tools. The first is large relation lemma. The second is top to bottom lemma. The first is a large relation lemma. have three assumptions. First, that we assume the positive elliptic algebra do not split. Second, we assume that delta has degree -2, and when it's reduced to a map from H4 to H2, the map must be non-trivial. We assume that's non-trivial. It's equivalent to say that the rank is at least 1. And the third says that there's no generator degree 6, no generator degree 10, no generator degree 14, and so on. And the conclusion is that we have a few relations with large degree, like degree 12 or degree 16 and so on. So one corollary says that the last relation, which is the maximum relation, UK, must have a degree at least 12. This lemma is very important because if the three parameters hold, the conclusion says that we will push up the formal dimension higher and we will reduce many discussions. And if the lemma do not apply, this means that some of the parameters are false. If the parameter 2 are false, which means that delta when reduced to H4 to H2, it must be wrong. So it means that we know some knowledge about delta. If parameter 3 are false, which means that we will have generator which in degree 6 or degree 10 and so on. This also means that we have large generators, and it means that we push up the formal dimension higher. So I will give a short proof of it. It takes 3 slides. The first slide is just a setup of it. From the landing 0 lemma, we assume that the degree 2 generator will be mapped to 0. And the first M generator with degree 4 will be mapped to the first M generator with degree 2. It's because we can change the basis of it. And we consider relations with degree 8. And we can write it as the tail of as the head Pj and the tail of Rj, where each Pj is a quadratic polynomial with the variables, degree 4 variables, and Rj is a polynomial with some degree 2 generators and with some the remaining degree 4 generators. And we choose a set J prime such as the Pj J prime is the basis for the span of pair terms in degree 8. Well, why is that important? Because that we can always decompose the relations into its head term and its tail term. Every time we apply a lot of derivation to it, the head term still remains, but the tail term just vanishes. And then we got some information about it. So this we did in this case 1. In case 1, we assume that the size of J prime is greater than or equal to M. Then for degree reasons, we can check that with some computation, delta square Rj, they all vanishes when the Rj has degree 8. And so the delta square Uj is just become substitution of it with 2 on the left. Since we know that delta square Uj has degree 4, we can count the degree. And because it will map something 0 to another 0, so this means that delta square Uj is in the ideal generated by U1 through UK. So equivalent, it says that the right-hand side, Pj, when the variable is substituted to be x1 through xm, this polynomial is in the linear span of degree 4 relations. Because degree 4 relation is the minimum degree, so it's a linear span of it. But on the other hand, we know something about linearly independent because we assume when we choose the set J prime, we assume linearly independent. So after changing basis, we can assume that the first M relations depend only on first M generators. But this precisely means that the pure model S star splits. And this contradicts to our assumption that they do not split. So these other cases, it's a case 2. It says that the J prime has size at most M-1. By the choice of J prime, we assume that the head terms of something not in the basis will become 0 because we can perform change of basis to subtract them. And we constructed an ideal. It has 3 parts. First, about some relation, some generator in degree 4, and all the generator in degree 2. And we can also contain the relations in the set J prime, and we also can include the relations with higher degree. And we can check that. We can check degree 4 is in the ideal when the relation degree 8 is in the ideal, with a relation degree 10, 14 is also in the ideal, and so on. So it turns out all the relations are in this ideal. So H star can be projected onto another quotient, which is the polynomial algebra taking quotient of I. Since we have already assumed that H star is finite dimensional, so its quotient space must also be finite dimensional. So from knowledge in commutative algebra, we know that the set I must contain at least k generators. So we can count that the first part L0 will contain the number of generator degree 2 plus the remaining of generator degree 4. So it's G4 minus M. The second part, by the assumption, this set is bounded by M minus 1. So we have M minus 1 here. And the third is just the number of relation degree 12 plus the number of relation degree 16 and so on. So at least as the last step, we have a sum of 3 parts and it's bounded below by K. So when we move the first two parts to the right, it means that we get a lower bound on the number of large relations. Let's finish the proof. So let me go back to the on this lemma. Do you have any question on the proof of this lemma? So I will continue to move on. The second new tool we prove is a top to bottom lemma. As the name describes, we have some maps that go to the top degree to the bottom degree. Well, we have 3 assumptions. First, we assume that do not split. And second, we assume that there's an upper bound for the largest relation, UK. So degree of UK is bounded by 3 times the degree of XK. And third, we assume that there is a map delta to raise to some power L, which go to the top degree, H to XK, and go to the H to X1, the bottom degree. And we assume that this map exists, is non-trivial, which means the rank at least 1. The conclusion says that the map has a rank at least 2. This lemma is a reminiscent of K minus 1 lemma, which says that if rank of delta is at least 1, then rank of delta must be at least 2. So both of these lemma exclude the case when the rank be exactly 1. Well, why is lemma important? Because if it holds, which means that there will be the rank at least 2 means that there will be at least 2 generators with top degree. So it will raise the formal dimension higher. If the lemma do not apply, so some parameters are false. If parameters 2 are false, it means that the relation UK will be at least 3 times SK. So it will also raise the formal dimension higher. If the parameters 3 are false, then either this map do not exist or this map is just trivial. So we get a lot of information on how the delta behaves. So this is the reason why this lemma is important. So the proof of it will also take 3 pages of slide. First, we do some setup. By assumption, we assume that the degree of delta divides the difference of the degree. We also fix some else, such as the delta to the power L mapped to the top degree to the bottom degree. We suppose by contradiction that rank is precisely 1. Then we can perform a change of basis, such as map xk to x1 and map the remaining term to just 0. We can construct one ideal, which contains only the generator from x1 to xk minus 1. For the same process, we know that h star is finite dimensional. So there must be some relation not in the ideal. Why is that? If all relations are in the ideal, then we can project h star onto a quotient, which is the polynomial algebra quotient by I, which should be also finite dimensional. But we care that polynomial algebra taking quotient of this I will be infinite dimensional. So there must be some relation not in this I. Also from probability assumption, second assumption, we know that there's an upper bound on the degree. So the real I must look at that quadratic term plus xk times some term plus the g. And then we can do some change of basis to do some scaling and replace xk so that at the last, we can have a very clear description. Ui must be xk squared plus another polynomial g prime. The g prime is a polynomial depend only on x1 through xk minus 1. So we apply delta to power 2L to the equation. The first case, we'll break it to 2 cases. First, we assume that delta 2L of the tail will be 0. So on the right-hand side, we see that it will be a non-trivial term times x1 squared, it's non-trivial. On the left-hand side, we know that there will be a relation with minimum degree. So it means that after changing some basis, we got the relation u1 prime, which only depend on generator x1. So u1 is a polynomial that only depends on x1, which means that h star splits, as it contradicts to our assumption that h star cannot split. And the other cases is that if delta 2L with g prime is not 0, then we can since we know that G prime is the sum of many monomials, and so there's one monomial such that the image is not zero. And use the Leibniz rule, we can expand that there must be some term that is not zero. So we will have this inequality here. Each term must be non-zero, so each term must have degree at least x1. So we consider its degree. We know that p times degree of x1 must be bounded by the degree of this part, so the degree of it. And on the other hand, the degree of this one is just the degree of delta 2L G prime, so we count this 2 times x1. So the final conclusion is that we know P is bounded above by 2. Since we also have pure model, P also bounded below by 2. So the only choice is that P equal to here. So we go back to this inequality here. This means that there exists some generator xi different from xi, such as when we apply delta 2L to it, it's not zero. This contradiction. Why is contradiction? Because it contradicts to our assumption is that, wait. Because it contradicts to our assumption is run at least one, contradicting to this part. So as we can see, we have two mutually exclusive cases, case 1 and case 2. They are exclusive to each other, but in each case, we both have contradiction. So this means that we have come to the point when we go to the left is wrong, when we go to the right is wrong. This means that our starting location is wrong. So this means that when we suppose rank is precisely 1, we have something wrong here. So they will just prove by contradiction. This cannot happen. So the rank cannot be 1, which finishes the proof. So do you have any question about this lemma? So if not, I will just go on. We use the new two tools to do some proof in the paper. So one part of the proof is a proposition 4.2. We assume that H star do not split, assuming that there's a non-zero derivation with negative degree. And further, we assume that the degree of the last two generators sum up to 10. Then it means that when the formal dimension is bounded above by 20, there's only one positive exceptional cases. We should look at that. And at the end, we prove that this case also satisfies the Halperin conjecture. But at this stage, we know that there's only one positive exceptional case. Look at that. So I will not give a proof detail, but you can see from the sketch that we almost use all the methods we have. So intensity applies that. Let me go through it step by step. So for the first line, since we know that the sum of degree go to 10, so there are two choices, degree 2 and degree 8, or degree 4 plus degree 6. If the former cases, then the k minus 1 lemma says that delta must be 0, so we rule it out. The only remaining possibility is that sk minus 1 at degree 4 and sk at degree 6. We use a strong algebraic condition. It means SAC. I will not give a detail, but when we apply that, it turns out that we only need to consider the situation when sk has degree 12. But sk has degree 12, which is smaller than 3 times degree of sk. So that means that we can apply the top to bottom lemma. Since there's only one generator in degree 6, so the top to bottom lemma fails, which means that delta through sk must be 0. It cannot be rank 1 or rank x2. That's not possible. The only possibility is that the delta through sk must be 0. And we apply the k minus 1 lemma to say that it cannot be 0 if we consider delta sk minus 1. So we can perform a change of basis so that the delta sk minus 1 is x1. So at this stage, we see that delta xk is a polynomial depend on x1, x2 through sk minus 1. But it cannot depend on sk minus 1 because if it depends, it will contradict to the case delta through sk is 0. And it will not depend on x1 because we can do some replacement. We replace xk to a new xk so that these delta xk do not depend on x1. So we see that it goes from x2 to sk minus 2. The conclusion is that the k must be bounded below by 4 because if it's smaller than 4, 0, this polynomial must be 0. And the k minus 1 lemma is that the derivation itself must be trivial. We cannot have this to happen. So we have two possibilities. First, that if k is greater than or equal to 5, then we use degree inequality to do some computation. And it turns out that the formal dimension is at least 20. Since we only need to consider formal dimension at most 20, so we take equality everywhere. And we build its degree type. Look at it has this form. We have two unknown. But we have pure model, which says that the degree of relation is at least degree of twice the degree of generators. So we can solve that. The only possibility is that degree of x2 equal degree of x2. So it is the degree type we have find that. If it turns out that if k is equal to 4, we use some technique to show that there's a contradiction. I will not give detail about that. It turns out there's a contradiction. So we intensively use almost all the lemmas, the tools, method, assumption we have to raise the situation down to one only possibility, only is degree type. So in the paper, we follow this strategy. We consider the case that when the sum of two loss generator is greater, smaller than or equal to 8, equal to 10, or greater than or equal to 12. And we have some exceptional cases. In the first one, we have 3 exceptional cases. The second one, as you have just seen, we have only 1 exceptional cases. And the third, we have 2 exceptional cases. Then we solve these exceptional cases one by one. And it turns out the Halperin conjecture still holds for these cases. And then we have three comments for that. First, that it turns out all the exceptional cases that we constructed have formal dimension 18 or 20, which means that even if we do not consider the exceptional cases, the Halperin conjecture holds up to formal dimension 16. So we have given a shorter proof of the Halperin conjecture up to dimension 16, which simplifies the work in Tina's recent paper. And the second note is that one case with formal dimension 20 has this degree type. And this one is pretty difficult because our previous method did not have many useful information when apply to that. And once for a while, we even saw that this case might be a counterexample. And luckily or unfortunately, it turns out it's not a counterexample. So the Halperin conjecture holds for this one. And that's why we stop here, because this degree type is a little bit difficult to deal with. And if the formal dimension is higher, 22, 24, there will be a lot of cases like that we cannot deal with. So if anyone wants to raise a formal dimension higher, it's my suggestion to focus on degree type, look at that, and build a method to deal with these cases. So that's why we start the formal dimension 20. So, and this is the reference. I finished the talk, so do you have any questions? I'm happy to answer.
Okay, so any questions for the speaker? Maybe clap to thank the speaker and then see if more questions. Okay, so any questions?
I have a question. Could you just say a little bit more about what made that difficult case
Sure.
particularly difficult?
Sure. This degree type is a little bit difficult because as you can see in the previous cases from degree 2 and degree 6, there's a middle stage called degree 4. So if we apply delta to it, they will map degree 6 to degree 4, map degree 4 to degree 2. So there's a middle like bridge connecting the lower degree and higher degree, so raise down possibility. But in these exceptional cases, there's no middle stage. The degree 6 directly go to degree 4. So there will be a progressive polynomial in the two variables, and there will raise many possibilities because delta x3 can be a quadratic, like something times x1 square, something times x2 square, something times x1, x2, and also the same thing for the second one. So we need to do lot of assumption to simplify the structure. So degree type itself is not very helpful for these cases.
Yeah, I think this is the only one where there's a jump like that. Isn't that right?
Yes.
Yeah.
For any of these cases, are you able to then sort of say what all the derivations have to be? I guess you do say what they have to be.
Yeah, we need to do some discussion.
You find the derivations.
Yes, we discussed that if the derivation is degree -2, if the derivation is degree -4, what might happen? Because the degree is a little bit low dimension, so we don't need to consider with the degrees -6 and
Oh.
yeah. Just
So you showed, that's right. So you showed that that can't happen and you show there are no negative degree ones. Do you find what are the derivations that are now of non-negative degree?
Yes, we suppose that there's a there's non-trivial derivation with negative degree.
Okay,
And
I
we
see.
show that there might be some contradiction, or it turns out that it's trivial.
Okay. So I guess the question of finding then the derivations, which would then be all positive or 0 degree, is a completely different question, right? So
Yeah.
do you, your methods don't give, because you assume there's a negative one.
Yes, completely different if we have positive.
Okay, I see.
That never
Can
crossed
you
my
tell
mind.
us, sorry?
That never crossed my mind.
Oh.
Yeah, I don't know any, just to jump in, sorry. Did you have another question?
Oh yeah, well, what's an example of a ring with this more complicated degree type? I guess I should just write down some variables and some equations, doesn't matter, right?
I did not write it because we only assume degree type. It's possible
Yeah.
the relation can look very complicated. It's always very simple. We have no restriction on that. So only
Got it.
degree type.
Okay, very nice.
Thank you.
Okay, any further questions? Okay, so I'll clap again. And right now, it looks like there's going to be algebra seminars for the next 2 weeks. Although I just found out that one of them is going to sort of conflict with somebody's thesis defense, so I'm not sure if I'll do anything about that or not. But right now, it looks like there's going to be algebra seminars the next 2 weeks. Okay, so okay, I guess that's it. Maybe you should try to stop recording
Sure.
if you know how to do that.